Okay, so hello and welcome everyone. In this video, I'm going to talk about the link between hypothesis testing and the normal distribution and what we're doing with this whole process. So the basic idea with hypothesis testing is we are going to stipulate some hypothesized center of actually a sampling distribution that's assumed to be approximately normal, or if we have a large enough sample, or that's known to be normal. Then we're going to collect evidence, and we're going to observe how consistent that evidence is with whatever was our initial or our null belief. So for instance, our null hypothesis might be mu is equal to mu naught, and our alternative might be mu is not equal to mu naught. This would be a two-sided alternative. We could also say mu is greater than mu naught, or that'd be a right-tailed alternative, or mu is less than mu naught, and that would be a left-tailed hypothesis. Here by mu naught, I just mean some value that we're just going to assume that it's our null assumption for the mean. Rather than mu's and means, we could do population proportion, and basically the same thing. What would change would be the standard errors, right? Okay, so typically we'll test at some stipulated level of significance. Here I'd say at the alpha is 0.05 level of significance, just so I've got something concrete. We are going to, in this case, obtain the sample mean. So obtain x bar, the sample mean, on the basis of a sample of n observations. And then we're going to find how close is x bar to that mu naught, and whether it's far enough to need to revise our null hypothesis. So basically what we do is we have some hypothesized value for the center of the distribution. Whatever that is, it's on some normal distribution. It's probably not the standard normal distribution. We'd standardize by converting whatever is mu naught to a z-score. Right? So you subtract off the mean, divide by standard error, or in the case of the sampling distribution, you'd subtract off the mean, divide by the standard error, and that would give us the corresponding z-score. I should actually have a negative here. This should be minus 1.96. I think I do that a little bit later on, so maybe I should just skip down to that one. And what we're trying to do is we're trying to find out where is x bar. So we have our hypothesized center of the distribution, and so we'll find the z-score corresponding to whatever was the mu that we were looking for. Then we stipulate our significance level. In this case, I said at the alpha is 0.05% level, so I'm going to put 5 with a two-sided alternative. This puts 5% in the tails, so 2.5% of the area in each tail, 95% of the distribution in the center. And then I'm basically asking, where is x bar? So where is my test statistic? So I'm going to convert this. Now actually this is a little bit misleading because we have to normalize. We have to convert this x bar to a z-score and locate it on the distribution. A number of standard deviations from the center. Notice on the standard normal distribution, this would be 0. This is 1.96 standard deviations to the right. This is 1.96 standard deviations below the mean. And then what we're asking, these are our critical values for the 95% levels, or the 5% level of significance that puts 95% in the center of the distribution. And basically what we're doing is we're asking, where is x bar? Where's our test statistic? Or where is the normalized version of the test statistic? If it falls closer to the center of the distribution than 1.96 standard deviations, we would fail to reject the null hypothesis. That could happen if it's along here or if it's along here. But if we have a more extreme test statistic, if x bar is normalized to a z-score that's greater than 1.96 or smaller than negative 1.96, then we'd reject the null hypothesis. And what this would tell us is, hey, there was only a 2.5% chance that our test statistic would be in this portion of the tail if our null hypothesis is true. So since this was very unlikely, it must be the case that the null is suspect. We'll have to revise our belief about the null. We probably reject our null in favor of the alternative. Right? So here's the one-tailed test counterpart to the two-tailed test I had above. So this would be at the alpha is 0.05 level. This puts 5% in the tail. Here's our critical value. And now I would reject the null if my test statistic was greater than this, than my critical value, if it's more extreme, more distant from the center of the distribution. So this would be the right-tailed alternative. So what's going on? Well, we have our normal distribution. We're assuming our sampling distribution is approximately normal, and we're trying to convert our sample mean to a z-score located on this normal distribution. I'm illustrating both our rejection region approach and then our p-value approach. So the rejection region approach says, well, if our z-score lies in this tail area, it's more extreme than this 1.96, for instance, then we'd reject the null hypothesis. Our p-value approach says, well, suppose, okay, so for instance, suppose x bar would convert to a z-score of 2.5. The p-value would be the probability of observing a test statistic that extreme or more extreme. So it'd be the area deeper into the tail. So I've illustrated here is my alpha is this area with this cross-hatched, and then this shaded over in red is my p-value. If the p-value is contained in your alpha in the tail, then you'd reject the null hypothesis because then p is smaller than alpha. So it's a smaller probability than our significance level. However, if the test statistic was here, then the p-value would be bigger than the tail area, than the alpha, and then we'd fail to reject the null, right? So I say, if the test statistic is more extreme than 1.96, we'd reject the null. We'd reject the null if the test statistic is more extreme than the critical value. This happens exactly when the p-value is smaller than alpha. Also, the p-value is the area toward the nearest tail from the test statistic. If p is smaller than alpha, then you'd reject the null hypothesis. So I think sometimes it helps to see this a couple different ways, and I think this is kind of a good way to think about it. Remember, the p-value is the probability of observing an observation at least as extreme as the one you've got when the null hypothesis is true. The p-value is going to be the area into the nearest tail from the test statistic. If the p-value is smaller than alpha, reject the null hypothesis. This happens exactly when the test statistic is greater than the critical value. So anyway.